So the motivation of this particular work comes from this numerical simulation that was performed with decaying Gross-Pitaevsky equation. In this particular case, what they were trying to establish, the connection between this quantum turbulence and classical turbulence, and calculated this intermittency using these quantum vortices. But I basically was mainly I got motivation from the fact that they basically analyze the things very nicely in one aspect, that what you can see here, this is the vortex tangle in the turbulent state, and this green and yellow represent the different polarity of the vortices. And if you look at this the 2D cross section of this the box, then what you see that there will be clustering of these green vortices and clustering of these yellow vortices, and that basically gives rise to Kolmogorov scaling. So after that, what they did, that they considered the vortex field by keeping the vortex position same, but by changing its polarity randomly. So that will make this mixture quite random. And this they call it GP discrete vortices in the disordered state. It means that its orientations are well mixed. And in that particular case, they get the different scaling than this Kolmogorov scaling, and they report the scaling to be k to the power minus 1. So in this case, they also calculated this spectrum using this Gross-Pitaevsky equation, as well as this Navier-Stokes equation, and they find perfect matching between this GP discrete vortices when it is in the turbulent state, but it is clustered like this. So this very much matches with this superfluid turbulence in presence of the rotation, where all the vortices get polarized, and we have this k to the power minus 5/3 scaling. So this scaling is quite well known in the field of the superfluid turbulence, where Wienen basically proposed this thing that if the vortex line density, which is this vortex line per unit volume, if it varies with t to the power minus 3/2, if it decays with this power, then energy spectrum will be k to the power minus 5, it will show Kolmogorov scaling. And if this vortex line density decay with t to the power minus half, then it will show Wienen-like scaling. So here we clearly see that depending upon the vortex the orientation or the vortex clustering, we have the different sort of scaling. In one case, when all the like polarity vortices get organized, then we have this Kolmogorov scaling, and when it basically get randomized, then we have this Wienen scaling. No, it's the vortex line density. So the number of total vortex line into volume. Yeah. So in this particular case, we observe the two sort of scaling, but this is a 3-dimension Gross-Pitaevsky model. Motivated by this, we wanted to basically test this kind of thing in our 2D simulation, and in that case, we have done the two sort of simulation. In one case, we have considered the rotating Bose-Einstein condensate, where we basically put the condensate as Makota mentioned that in the trap, and then we add some perturbation and generate the different configuration of vortices, and further we analyze that if we have the different configuration of vortices, what are the energy spectrum and fluxes. So for that we consider two sort of cases. In one case, we have this no vortices present in the beginning, and then we slowly ramp this rotation and generate the vortices in presence of the perturbation, and the system become quite turbulent, and we observe this shows Kolmogorov kind of a scaling, and for this case, Vortex lattice gate shows 1n kind of a scaling. We don't have this the answer at present, but I will try to convince you that we have a little bit contrary observation that was obtained in the case of 3 dimension. Then, if time permits, I'll talk about some of our recent work where we, instead of giving the rotation, what we have done that we have considered the particular configuration of the different polarity of the vortices and look at the energy cascade behavior as observed in this case of the 3 dimension the Bose-Einstein condensate. So with this, I just already Makota basically gave very nice introduction. I just rushed through this preliminary just for completeness that Bose-Einstein condensate when the particle de Broglie wavelength become of the order of interparticle separation, and due to that particle loses its individual identity, and we they have the situation when all the particles become indistinguishable, and that can be represented by a particular giant macroscopic wave. And this led to a couple of Nobel Prize, one to get this the laser cooling, and another one to observe the Bose-Einstein condensate. And this is a typical velocity this is a typical particle distribution in the Fourier space. High temperature higher than the condensate, and when it reaches to the condensate temperature, then you can see particles start approaching towards this zero momentum, and at temperature below critical temperature, all the particle goes to the zero momentum state. So in this way, the vortices in BEC are just the topological defects that being generated by the external means by several techniques, as in a previous talk it was mentioned, by phase imprinting with applying some obstacles or giving some rotation to the system, and it is quantized in nature in the quantum turbulence, and the density at these vortices becomes zero, and there is a phase discontinuity as you basically move in a circulation. So in the BC, if we put up a trap and then we start rotating it, then there is a wave generation at the surface, and finally that basically generates some vortices, and it is being pushed in the bulk, and for a given trap we get a very nice lattice structure. So this is the situation for dipolar BEC, where one can see that these 7 vortices form this kind of lattice structure. And what we can see here, that as we increase the rotation speed, then this number of vortices keeps on increasing, but it retains this lattice structure. So for a trapped BEC, we cannot get the turbulent state, and for that we need to basically add some perturbation, and that's a quite challenging task because each perturbation will not give you the turbulent BEC. So in this particular case, this is our dynamical model for the rotating Bose-Einstein condensate. So this is kinetic part, this is the potential part, this is the interaction, and this is the rotation. This is the rotation part. So here what we do, that we consider this potential, which is a mixture of 2 sort of potential. One is harmonic trap, just to confine the condensate, and another one is the barrier. And barrier, we have this sort of nature that it is constant. But it depends upon the angle at which we are. I will show you the detailed picture of this perturbation. Otherwise, it is zero. So what it basically does. So here I show the typical the velocity, the typical this this potential the diagram. So here we have the two sort of potential. One is of big arm and another one is the short arm, and this is having the and this varies periodically in nature with the sine theta function. So what it will do that the potential is very high and constant. So in that case, it will try to generate the vortices, and if the vortices are already present, then it will try to pin the vortices at this value. So we have taken two sort of perturbation. In one perturbation, this alpha and beta, it means that the period for this bigger arm and for a small arm, that is rated with if alpha is 10, beta is 20, it is related it is biperiodic. But another case we have considered that this alpha beta relation is golden mean ratio. Just to check that if we get different sort of turbulence behavior, or we get the same sort of turbulence behavior independent of the perturbation. And so this is the typical methodology that we use for our the system. What we do that we first consider the different initial states. So here we have the condensate, and then we switch on this perturbation. So you can see here that wherever a perturbation, when there the condensate density becomes 0, and then we ramp this the rotation with this particular function. So this TR we consider it to be 120. So slowly with this the function with the initial omega naught that we generally consider 0 for vortex-less case, we ramp this perturbation, this rotation speed, and as it reaches to the final value at t equal to 120, then what we see that there are perturbation that starts appearing on the surface. Also, this some role is played by this perturbation that you can clearly see here that it tries to pin this some sort of vortices. So there is a combined effect of the rotation as well as the perturbation that finally leads to this kind of turbulent state for the Bose-Einstein condensate at a very long time. So this is a situation when we don't have any sort of vortices at the initial state. Then we consider this state when we have the vortex lattice, and that we generate using the imaginary time scheme by giving some frequency which is critical value, which is above the critical value, and we generate this sort of vortex lattice. So you can here you can see that these are vortex lattice that we generate, and it get pinned to the some of the arm of this perturbation, and then we start increasing the rotation. So as we increase the rotation at t equal to 120, what we see that the vortices basically get merged, and it forms this sort of bigger vortices. And as we keep on continuing with this final value of rotation, then what we see here that finally it reaches to the state where this vortex basically will get mixed, and also it interacts with this condensate and creates the turbulent condensate. This is a typical this is a typical angular momentum through which we confirm that whether our system has reached to this steady state. So what we basically see that we have this omega final 0.91, 1.1, 1.2. So we also go above 1 in this case, and that we see completely different behavior that we will discuss in detail for this vortex lattice case. So what we get here that as we keep on increasing value of rotation, then this angular momentum keeps on increasing at the steady state value that confirms the increased number of vortices. However, we are not quite sure that how the turbulence basically arise in the system, what is the contribution coming out from this rotation, and what is the contribution coming out with the application of this perturbation, this sort of perturbation. So
That frequency is in units of the trap?
Yes. So, we have this transverse trap through which we make this 2D. So, we are going above that trap. So maybe we are exciting some mode that we are not, but I'll show you that we are getting different sort of behavior due to that. So, then in this particular case, we calculate the spectra and fluxes by decomposing the condensate kinetic energy into compressible and incompressible parts. So the incompressible part mainly contains the contribution from the vortices, and compressible part contains the contribution from the acoustic wave. Then we make this Madelung transformation weighted by this velocity that will make this velocity regularize at the core of the vortices. And further, we basically decompose it into the several contribution of the kinetic energy. This is the incompressible part, compressible part, and the quantum part. And we compute this kinetic energy spectrum by the method proposed by Bradley recently using this Wiener-Kirchner theorem, and we use this Julia package to compute our energy spectrum. In this particular field, especially in this BEC turbulence, people don't know at present how to compute this flux. But there are some flux calculation that is quite popularized, and we have used that, but that is not giving us the clear picture. But nevertheless, we have used that, and we get some the preliminary picture out of that. So here we define the flux as the rate of change of this incompressible kinetic energy, sum over the k0 to k. So that will give us the flux at k. So we can keep on varying the k value and can get the flux in the Fourier space. So here the positive flux will mean that we have this forward cascade, and the negative flux will mean that we have the inverse cascade. So now coming to the kind of configuration that we basically started with. So first we will discuss the observation related with the vortex-less initial state when we don't have any vortices present at t equal to 0. So in this particular case, what we notice that if omega final is less than 0.8, then we don't get any sort of excitation of this the vortices, or even it get excited, we get few vortices, we don't get turbulent state. But if we keep on increasing this value omega final greater than 0.8, then we get this turbulent condensate. And using the formalism developed by Aston Bradley group, we compute this the incompressible kinetic energy. So what we saw here, we saw the incompressible kinetic energy normalized with the chemical potential for different rotation rate. So this one is 0.85, 0.95, 0.99, and this one is for omega final equal to 1. So what we see here, we see that in the range in the scale which is lesser than the Healing length, in that case we get the spectrum due to the vortices, and that matches with k to the power minus 3 scaling very much. So that is quite confirmed in all the cases. So that finally confirms the situation that in vortex lattice case, finally we have the formation of good vortices, and we confirm it by observing this sort of scaling. When we look at the scaling between the Thomas radius and Healing length, the Thomas radius is just the length scale which is decided by the trap potential. So it is larger than the Healing length and decided by the length scale of the trap potential. So here what we get that the scaling behaves with k to the power minus 5/3. the same sort of scaling, and that scaling becomes more and more pronounced as we go for very high value of omega. So here, for example, for 0.99, we get this is the scaling range, but for 1, we perfectly get that it becomes it is quite matching with this Kolmogorov scaling. So what we basically observe here, that initially we don't start with the vortices, and then with applying the perturbation and rotation, we have the turbulent configuration of the vortices, and that shows this sort of Kolmogorov scaling in this inertial range, and this is also known as infrared range. So confirming the kind of cascade that we get for this Kolmogorov scaling, we compute this the kinetic, incompressible kinetic flux again for the different the rate of rotation. Here we find very interesting, but nevertheless people know how it is coming. What we get here, that flux basically fluctuates between positive and negative value. So here this color bar shows this different time at which we are plotting our flux. So it is higher than the time when a system reaches the steady state. So we are plotting this flux for starting from 200 to 400. And what we see here, we see the systematic change in the flux the value from positive to negative. And this frequency is coming out to be the same as the breathing mode frequency of the condensate, and this is true for all the cases. So in this particular case, what we do, that we consider the very long time average of the flux behavior, and that basically gives us the hint that we are getting positive flux for all the frequency range. So although we are getting the Kolmogorov scaling in this particular case, but flux that we have computed, it gives us the indication that in cascade behavior here is forward in nature. And further, what we do, that we also compute this compressible kinetic energy for the same initial condition for all the rotation rate. And what we observe here, that in the infrared range, the system get thermalized, and it spectrum behaves with k for all the frequency range. But in the range of Vortex core, what we get, that is scaling is k to the power minus 7/2, and generally Jakarov basically predicted that this scaling will be k to power minus 3/2 for 3D. But we don't know that why it is coming k to power minus 7/2, because we are using perturbation, or it is coming due to the rotation. But nevertheless, we get this k to power minus 7/2 for this particular case. That at present we don't have any explanation or way or theoretical tool to understand this thing. So then further we move to the situation when we have the initial state, which is the vortex lattice state, in which vortices are arranged on a hexagon lattice, so that we generate, and then we basically create this turbulent state. Again, one interesting thing we find here, that if we go the final frequency greater than the transfer trap frequency, then we get some sort of clustering of the vortices. So here what we can see, that this rate curve is 1, and the number of vortices being created for omega f equal to 1 is higher than the 1.1 and 1.2. So that is quite interesting feature that we observe from this particular behavior. And earlier I was talking with Paulo, and he mentioned that this may be connected with this some sort of excitation of this condensate in the Landau levels. But we observed this thing, and we first didn't rely over that, and we reperformed our simulation and further we run it for the very long time, but it sustained for omega f equal to 1 for this vortex lattice case. This we didn't observe for vortex less case. That was not a problem. But for this, when we start with this particular configuration, then we get this sort of interesting feature. So further we computed this the incompressible kinetic energy for this particular initial condition. Here again, in the ultraviolet region, it means that the length scale lesser than this the healing length, we get k power minus 3, that is consistent that we get the vortices. But in this infrared range, we are not getting this Kolmogorov scaling. It is more closer to this Winen scaling. It appears to be k to the power minus 1 for all the rotation rate. And again, as we go for high and high rotation, this k to the power minus 1 scaling becomes more and more prominent. What we see here, we get this totally opposite behavior that we were expecting for 3-dimension turbulent BEC. In 3-dimension, if vortices are polarized or it is getting aligned, then scaling was Kolmogorov. And if it is randomized, then scaling was Winen scaling. But here, with this particular initial condition, when we start with the vortex lattice, we get this Winen scaling when vortices are getting polarized. So, at present, with this, we also computed this kinetic flux, and that basically shows again the forward cascade of these vortices, except these small glitches sometime, but again, this depends upon that how long we average over the time. So, overall, again, for this initial condition, although we get this different scaling for the incompressible kinetic energy, that is Winen scaling, the cascade nature is forward in nature. If we compute this compressible spectrum for this vortex lattice case, here we very nicely get that in the infrared range, the scaling is k to power minus 3/2. That was predicted by Zakharov using the weak wave turbulence. And that is consistent also because Winen scaling is observed due to the Kelvin wave propagation along the vortex lines. And here, this consistent thing we get even for point vortices. So, for all the cases, this ultraviolet regime, we get k power minus 1/2, but for infrared range, we get k to power minus 3/2. So this suggests presence of some weak turbulence when we are getting this Winen scaling. But here the things dramatically change if we go for this final frequency exactly equal to the transverse trap frequency, because this is the things that we notice that this is the density picture for omega f equal to 1. And what we get here that in this case, in the infrared range, the scaling basically goes like Kolmogorov scaling. So that is quite interesting that for same initial condition, if we have the rotation which is lesser than the transverse trap frequency, we get this Winen scaling. But if it is exactly equal to this the trap frequency, then we get Kolmogorov scaling. And that basically tells us that there may be some something is happening at this particular frequency. But right now we don't know that how to disentangle the contribution coming from the rotation and this perturbation in order to understand it in a better way. So with this, I just like to summarize this part of the work, where by selecting the proper perturbed central barrier, we have been able to generate the turbulent behavior in condensate for when it is trapped under the harmonic potential. And what we basically see here, that a strong perturbation can trigger the formation of ordered vortex lattices from a free condensate, and that is scaling we are getting Kolmogorov scaling. And in contrast, for vortex lattice case, the energy spectrum scaling is coming out to be Wien scaling. What we basically again notice here that if the frequency is same as the transverse trap frequency omega equal to 1, then vortex lattice case scaling becomes Kolmogorov. So all of a sudden for this particular frequency, how we are restoring back to this Kolmogorov scaling, that answer we don't have at present, and we would be like to explore this in a more elaborated way. So overall, using this particular perturbation and rotation for two different initial conditions, we have been able to notice this two different behavior of the cascade, and which appears to be same as reported in the 3 dimension, although not in the similar fashion, because here the vortex nature is point vortex and there it is the filament. So continuing with that, what we plan that since here things are becoming more complicated, that the rotation and the perturbation that that are responsible for this the turbulent behavior, just make the things more simpler. What we do that we inject the vortices in the system with phase imprinting, and we consider a different configuration or different configuration of the vortices. So here red one basically denotes this up vortices, and the blue one denotes the down vortices. So here we consider this dipole kind of a structure, and in B we consider this positive and negative vortices are randomly distributed, and in this case this one sign vortices are in the cluster, and then again we consider that the lattice of these positive and negative vortices. And if we look at this thing detail, that what will happen to this thing by evolving it using the Grosspita-Ski. So in dipole case, what we find that this vortex and anti-vortex get annihilated, and that generates this sound mode, and finally it reaches to the state when a few of the vortex anti-vortex remains, and that remains for a very, very long time. So in the second case, when we have the random configuration of the vortices, again here vortex and anti-vortex get annihilated, but we have the more number of vortices that will sustain after very long time. But if you look at these cluster vortices, here interestingly what we find, it will always remain in cluster, and that will keep on going forever. But this is not the true for the vortex lattice case. Here vortex lattice get unstable, and then we get this completely random configuration of vortex and anti-vortex. So further to just to summarize this thing, that this is the final stage the configuration of vortex that we get, where we have a two vortex and anti-vortex pair sustained. But in this case, for random case, we have the many vortex anti-vortex sustained, but it remains it is not forming any pairing. And in this case, it remains always in the cluster, and in this case again it forms this random cluster. So if you look at this the energy, how it evolves with time, the total energy remains constant, and what we can see here, this compressible part of energy becomes constant after some time. So we get the stable configuration of the vortices after very long time in all the cases, dipole, this plasma, clusters, and lattice cases, and that further basically force us to get into that energy spectrum behavior. And here what we get, that if we have the pair of vortices present in the system, then we are getting this sort of Kolmogorov scaling for this case. But if we have this random clustering and lattice the structure of the vortices, then at the final stage we get this the Wien scaling. So this one is consistent with what was observed in the three-dimension simulation, because in that case you can see that when vortices are randomly oriented, then we have this restoration of the Wiener scaling. So in that way, it tells us two stories that if we generate the vortices using this rotation, then we have the different sort of the behavior arrangement of the vortices, and that lead to different behavior of the scaling or energy cascade. But if we generate, remove the rotation, remove the perturbation, and simply start with this phase by injecting the vortices, then we have the same feature as was observed in this three-dimension simulation. So there are further works are required in this last case in order to make the connection with this whatever we observe with the rotation case, and that we are planning to get some idea by using some large scale mode present in the system, how it is exchanging the energy. And finally, we would like to develop some tool which can compute the flux in the better way, the same mode-to-mode energy transfer way that we have in the fluid dynamics. So with that, I would like to thank you all for your kind reference.
Questions?
Thank you for your talk. Nice talk. Yesterday you showed me some of these movies. I enjoyed them very much. So you have a kind of universality classes, I could say so. Maybe it's a little bit exaggerated to say so, but I mean, so if you start with a square lattice, you have an exponent. If you start with some Poisson distribution, you have another exponent for this, for the energy spectrum. I wonder if you, I mean, that could be interesting to check with the other kind of lattices, for instance, triangular lattices with different symmetries, to see if the exponents change and how they are connected to the initial configuration. I don't know if you have tried that or.
No, we already tried with this
the square lattice.
Triangular lattices.
Okay.
In that case, we get a similar stage that we have here.
All right.
So it get randomized because the lattice structure is not a stable one.
Okay.
In this particular case.
All right. Thank you.
Yeah. So in your plot of time evolution of energy, I think, it looks like if you run it for longer, especially for the cluster case or even for the dipole gas, I mean, the things would go down and the different energies would become same. So, you know, are there oscillations present in the system which you have to run for long enough to capture those, or, you know, different energies become equal? You have some idea on that?
Yeah, so we run it now for 10 to the power 5 time unit, and we get that similar behavior, that this energy, individual energy become constant. There is no exchange between the energy at the large scale.
Okay, and the second question I had was that these are constant energy systems, right? Right? And you are doing it with a spectral method. So if you run for long enough time, why there is, I mean, does the system ever go into a equipartition?
That's a good question. That's the thing we don't know, because what is happening, this vortex anti-vortex forms some sort of pairing. Okay, and then you can see if it forms the pair in such a way that it can only move in the straight way, then there is no chance of any reconnection. If that didn't happen, so it will go forever. So the configuration is forming in such a way that it becomes stable. It appears here like that. It remains to be stable.
All right. Thank you.
So we are not getting thermalization. So that aspect we are also trying to explore. That indeed we are getting non-equilibrium kind of.
Large K, what is giving you like in your spectrum? It looks like a power law which is going down.
Yes.
So is there something which is dissipating at very large, or it would grow up?
So in the incompressible part, this spectrum is coming due to the vortex pole.
Okay.
So there is no dissipation. So only source of dissipation that if vortex anti-vortex will annihilate, it will limit the sound wave.
In the rotating case, You compare omega with the frequency of the trap.
Yeah.
So have you tried comparing omega with the creep inside the first vortex in the lattice?
First vortex.
So there is so you have a quantum of circulation, and if you equal that to the circulation coming from the rigid body rotation,
Okay.
there is a minimum value of omega to excite the first vortex in the lattice. So that's also an important parameter in this system.
But that, how will you know? That's the
Oh,
thing.
it can be computed just from Thomas Fermi.
Okay.
Yeah, I
Okay.
can. Okay.
So,
More questions? Okay, so let's thank the speaker. Let's thank all the speakers of the morning.